Alright, this will be the Chapter 15 notes for first year chemistry on the chapter that deals with ionic bonding and ionic compounds. These are the notes that we cover in class. Just a quick summary of what we do. First I give the definition of an ionic bond. It's formed when a metal transfers the valence electrons, which are on the outermost energy level. They transfer their valence electrons to a nonmetal, and when this occurs, the metal becomes positive, which is called a cation, and the anion is the negatively charged atom, which is from the nonmetal. So we have a positive cation and a negative anion, and they bind the compound together. In our last chapter we did covalent bonds, and the reason they stick together is because they're sharing electrons. Well, in this chapter they're transferring the electrons from the metal to the nonmetal, and so there's a different force that binds them together. And if you want to represent the ionic bond, you can just show the electron from the metal moving to the nonmetal. And so I have the one valence electron for sodium, and it moves to the outer shell of the chlorine. And when this occurs, the sodium is now completely full as the noble gas neon. It has the configuration 1s2, 2s2, and 2p6, and so it's stable. And chlorine, when it gains the electron, looks like argon, and so it again has a full octet of electrons. On the next slide, we do the dot notation. We have one valence electron for sodium and 7 valence electrons for chlorine, and again, the sodium electron is going to be transferred to the chlorine, and when that occurs it has a +1 charge, and we put it in brackets to signify that this is going to be a dot notation. And the chloride ion has a -1 charge, and since it's again a dot notation, we have to show all 8 dots. Now the next part of the notes, we do a couple practice problems. One that's a reaction between sodium atoms and oxygen atoms, and sodium has 1 dot as we had before in the top of the slide, and oxygen has 6, so it ends up that you need 2 sodiums for 1 oxygen. And sodium will still have a +1 charge, but there are just 2 of them, and oxygen will have a -2 charge. And it was too complicated to do the animation, so I just drew this on the chalkboard. In the next practice problem we have magnesium and fluorine. Magnesium has 2 valence electrons and fluorine has 7, so you'll actually need 2 fluorines in order for it to be a stable ionic compound. So magnesium will have a +2 charge when it loses both of its valence electrons to 2 fluorines. Each fluorine would have a -1 charge. On the next slide there's a little cartoon. And then we did practice problems just drawing the dot symbol for an atom versus the ion. The potassium atom has 1 valence electron. The potassium ion has no valence electrons anymore because it lost the electron, so it has a +1 charge. The sulfur atom starts out with 6 valence electrons, and when you have a sulfur ion, it will gain 2 extras, so that's why it has a -2 charge. And because this is a dot notation, we put the valence electrons around it, and it should always have 8. So in this chapter, the metal is always empty and it has a positive charge, and the nonmetal is always full with 8 dots, and it has a negative charge. On the next page we go over the difference between ionic compound properties and covalent bonded atoms, and they're called molecules, and their properties. Ionic compounds are conductors of electricity when you dissolve them in water or if you melt them, and they're formed between a metal and a nonmetal, and they have high melting points because the ions are very strongly bonded together, and so if you have a strong bond between the ions, it's going to give it a high melting point. If it's a weak bond between the elements, it's going to be, or a weak bond between the molecules, it's going to be a low melting point. That's on the next slide. And they're usually very soluble in water because there are positive and negative charges in the ionic solid, and there's slightly positive and slightly negative charges in the polar water molecule. And so the picture on the right side shows a green chloride ion being surrounded by the water molecules, and the black sphere is the hydrogens, and they have a slightly positive charge. So you have a gang of water molecules surrounding the chloride ion, and you have a gang of water molecules surrounding the gray sodium ion. But if you notice the blue part, which is representing the oxygen, the blue part, which has a slightly negative charge, is attracted to the slightly positive charge of the sodium, and so that's dissolving. And I say to the students that they form crystalline solids, and some examples of crystalline solids are on the next slide. And again, the picture on the right is just salt dissolving in water. And there are some crystal patterns, and we cover more of these in AP chemistry: the simple cubic, face-centered cubic, and the body-centered cubic. We cover them in second year chemistry and AP chemistry, but we don't do much with it in first year. And this slide shows the properties of molecular solids. They're insulators of electricity, and they're formed between 2 nonmetals, and they usually have low melting points because the dispersion forces and the dipole interactions, these van der Waals forces as they're called. I was going to say London dispersion, that's what they're called in AP chemistry, but in first year chemistry we just call them dispersion forces. But anyway, these are weak intermolecular forces that bond one covalent molecule to another, and since they're weak forces, they're easily broken, and so molecular solids have generally low melting points. And then the last property is the solubility of water varies for molecular solids. If you're a polar molecule, you will dissolve in water because you have slightly positive and negative charges that are attacked by the water molecule, just like the sodium chloride ions were attacked by the water molecules. If you're a nonpolar substance that you don't have these charges, you're going to be insoluble in water. And then we end the lecture with an explanation of what needs to occur to conduct electricity. You need charged particles, which are called ions, and they need to be free to move around so that the charge can actually flow through the substance. So it has to be in the liquid phase or the aqueous phase for a compound to conduct electricity. And then on the last slide, I do a demonstration with this light bulb apparatus where we have pure water being a non-conductor, and then I use Windex, which is a poor conductor. It does have some ions, some ammonium ions in the water, and so the light bulb glows just a little bit. If you had just pure sugar water, or just plain old sugar water, I guess it's not pure sugar water. Since sugar is a molecule, it doesn't have charges, and so it's a non-conductor as well. A good conductor would be any type of salt that dissolves readily, like table salt. It makes the light bulb glow the brightest. So those are basically the notes. It only takes one day to cover, and we do a couple chemthink.com computer activities, specifically the one on ionic bonding. So this is a very short chapter, and so basically our test is really a quiz because it's not very long. So those are the notes.